Hello and welcome. This is Chapter 2, Section 6 on inclined planes. It's another application of the equations of constant acceleration. This is another instance where there's constant acceleration, sliding an object down a smooth incline. So what is the formula for the acceleration of the object when it slides down one of these things, and how do we know it? Well, there's a couple different ways that we can answer that. First, you can invoke the experiment, right? You do the experiment, you make the motion diagram, and you observe what it is. You can change the degree of the incline, and you find that it scales not with the angle itself, but with the sine of the angle. That's certainly experimentally satisfying. Like in figure A right there, in figure B, we have this idea of, well, what happens if it's on an incline and then suddenly the incline disappears? Well, then it'll instantly go to an acceleration that's vertically downward, because in the figure above, the acceleration is not vertically downward. The acceleration is along the direction of the incline towards the down, if that makes sense. And so the trick is that you break the acceleration, the free fall vector, acceleration vector, into a part that points parallel to the incline and a part that points perpendicular. We'll talk much more about that in Chapter 3 and also in Chapter 5 when we talk about the forces behind this. But needless to say, the book argues that the perpendicular acceleration is somehow blocked by the inclined plane, and so the only part of the acceleration that contributes to the motion is the part that is parallel, and that part is also sine of theta, g sine theta rather. Another thing about that's, what is that angle? That's the angle that's given with respect to the horizontal, and if it is a positive angle, then the acceleration, it's going to be negative either way, whether it's a positive or negative angle. So if you have the length of the track, if you were doing an experiment and you know the length of the track and you know the height difference between the top and the bottom parts of the track, you can use that data as well, the difference in the heights divided by the length, because that's what sine theta is. That sine is the ratio between the opposite side and the hypotenuse. So that's another way if you don't have an exact angle. And that's one really deep problem-solving strategy that we'll want to learn in time, is how to do problems with sines and cosines and tangents without explicitly knowing the angle. Okay, so in the next slide, it's a long stuff about thinking graphically. And this is a really interesting problems where you just have a ball and it can go up and down different inclines, and that will affect the accelerations and the velocities and even the positions. Okay, so one thing you have to assume is that the ball passes smoothly from one incline to the next, right? There's no bumping, as you would expect when you go from like flat to straight up. Or not necessarily straight up, but up and on incline. Graphs, the graphs have no numbers, but they should also qualitatively show, and technically, the graphs of velocity aren't technically in the same vectors in the same direction either. That's a subtle point, one that we can appreciate when we've gone through some examples like this. So in looking at this example, what does the graph look like of the position, velocity, acceleration? Well, the acceleration graph should be pretty clear, right? It's going to be 0 until it reaches that downward sloping incline, and then it'll jump down to a finite negative value, and then it reaches the bottom, and then it'll jump back up to 0. But here's where it gets interesting. What's the velocity versus time graph look like? Well, the velocity versus time graph is, at the start, it's a small velocity, And then the velocity increases linear to a large velocity. So it turns out, if you study these graphs of these tracks, look what happens to the velocity versus time graph, the one in the middle there. It's actually a mirror image of the shape of the object. That's really interesting. That has some, that's kind of true in general about the velocity versus time graph, when you're making this assumption. So again, we see the acceleration graph. The acceleration graph is 0, followed by a negative, followed by a 0. That's going to give that mirror image graph for the velocity. And then the position, we've got a parabola, or we had a straight line, and then a steep straight line, and they're connected by a parabola in the middle. Notice how, and there's probably a remark that this makes, notice that both those dotted lines, or those dashed lines, the dotted arrows that point to those, notice how the slopes are the same on either side. The slopes are the same for each of those points. The slopes are the same on either sides of the dashed line, because the velocity or the position graph has to be differentiable, because the acceleration suffers a discontinuity. So this is a really interesting one. Well, now let's turn the problem around and ask ourselves, well, if we're given the graph, what should the thing look like? And don't immediately say that, well, it has to be a mirror image of velocity, because what's going on here? Now, it's not just a mirror image, because look, in the velocity versus time graph, you're moving to the right, and then you slow down to a stop, turn around, and then you're moving to the left, because the location of the curve in the graph in the v versus t axis coordinate system matters. If it was all above or all below, that'd be a different shape. And so this one has kind of it has, what would you think it does? I mean, it's moving to the right at high speed, slows to a stop, and then increase speed, and then it's moving to the left at high speed. So really, it just comes in and it has one upward track, and then it turns around. So exactly like we've got in that figure to the right there. Of course, the acceleration, it's 0, -0. And what about the position graph? Well, now there's an origin, but that it'll cross, but keep in mind that we still have the position versus time graph, we still have the slopes being identical on either sides of both of those dashed lines. The slopes have to be the same on either sides. Okay, so inclined planes is just another example of equations of constant acceleration. You have to just change the specific acceleration that you're dealing with. And oftentimes these fun track problems can really force us to think about what's going on graphically. So that's it for this video. In the next section, we'll conclude chapter 2 by giving an advanced topic of what happens when acceleration is instantaneous. As usual, thanks for your time. We'll see you back here on the next one. Take care.